right, hello, good morning, everybody. We are looking today at separable equations, which are another class of first-order equations we can solve by hand. These are the ones you want, okay? These are the ones that we can do very easily, and they're easy to identify. And typically they're quite easy to solve. I guess it depends on the integral. But the way that you know it's separable, an ODE is separable if it can be written in a certain way. So if you can have u prime of t equals g of t times some h of u. So as long as you have the derivative on one side, this is a first order equation, right? First derivative on the left side, and then on the right you have something in terms of t and something in terms of u, and these are being multiplied together. All right, so the reason that that's nice is you can easily split it and solve by integration, okay? So let's look at some examples of ODEs that are separable. So something like this. U cubed times ln of t. Is this separable? Well, I have a, h of u, and I have a g of t. All right, this function's only of u, this function's only of t, so it's separable. So yes, this is. How about u prime equals tangent u sine of u? Say, well, I've definitely got a function of u here. I could call this all a function of u, or h of u. But I can't see a function of t. Does this count? Well, it does, because you can just write, this is times 1, and we can call this our function of t, right? So this actually is separable. And this is a trick we'll use a lot, is maybe there is no function of t on the right-hand side. We'll consider 1 to be that function of t, and then separate it. Excuse me. Third example. U squared plus t cubed. Seems like a meek and unassuming equation. However, this is not separable. Why is this not separable? You cannot write it as a product of u and t because this is a sum. So this, is what breaks it down here. Maybe I'll use red to highlight that. So this is the issue. So it cannot be written as a product of two functions, no matter how you deal with that. Now, if you can factor it and make it happen, cool. But this is impossible to do. Okay, so usually it is quite obvious if something is separable or not. It's either looking something like the first two cases. All right, so to motivate this topic, something that we care about, objects in motion, the falling object. Let's talk briefly about this ODE, and we'll go to solve it. I'm going to leave the nitty-gritty part as a reading, just so we don't get bogged down in the video. But let's jump in. We'll see why this method is helpful and solves equations that we might care about. And we'll do another example after that to really highlight the process without getting bogged down, as I said. Okay, so again, in why I said differential equations is the language of the world, language of reality, and it's so easy to express these things. It's very easy to express how things are changing. It's easy to express what's happening to a falling object. It's much more difficult to describe exactly what a falling object is doing at a given moment. Okay, but it's very simple to model the forces on an object. So let's say we have, some object that's falling. It's heading in this direction, has a certain velocity. And so, we don't know what this velocity is at time t, but we can talk about the changes on this velocity relatively easily. We know that the net force is an easy way to understand what's happening. in terms of change, and then maybe generate some quantities from here. So the net force, the forces acting on this object, is going to be what? Well, what forces do you have? You have, if something's just falling in space, you have the force due to gravity, and then you will have some sort of resistance, air resistance, if there's a medium on the planet that you're on. So there will be some force of resistance here. And that's really, if as long as there's no other forces, this thing wasn't propelled in a certain direction, this is as good as you get. So this is kind of the model we're working with here. Again, easy enough to describe the situation without getting into the particulars. So a couple things. Force due to gravity, we know that this can be given by m times the gravitational constant, right? And then the resistive force, a common way to model this is that it is proportional to the square of velocity, which is helpful. Okay, why that's the case, I'm not going to get into. There is some motivation within the text if you're curious, or I'm sure you can do some research here. I just don't want to lose the thread. But it's proportional to the square of velocity. So here we'll be using mg, proportional to square of velocity, and it's going to be in the opposite direction. So we'll use a negative k for our proportion times the square of velocity, just kv squared. Okay, so then we have a pretty good model. We have the net force is equal to mg minus kv squared, and now we have something that relates to the speed of this object. And lastly, we'll tie in, Newton's second law. We know that F is really ma, right? Mass times acceleration is mg minus kv squared. And working through this, again, we just divide by m everywhere. We'll get a equals g minus k over mv squared. And you might say, well, Mally, we don't really have a dE yet. And I would argue, yes, we do, because what do we know about acceleration? Acceleration is really dv dt, right? So dv dt equals g minus k over mv squared. Now here is a relatively simple ODE that we just came up with, and we'd love to be able to solve it. We note it is first order, right? We note it is ordinary, but it is, so it's ordinary, it's first order, but it is nonlinear. Why is it nonlinear? Because we see that v has a power of 2, right? It is nonlinear. So that means that our method from before, the integrating factor, won't work. So we're going to need something else. Right, we can't kind of snap this ODE into place using that integrating factor. So what we can do, I'm going to start it and then stop. So what we can do is start with, okay, you've got dv dt equals g minus k over mv squared. What we can do is what I said before. We'll treat it like this one here. There is no function of t on the right-hand side, really. But we'll treat this whole thing as a function of v, and h of v, times g of t being 1. And then we'll divide this all over to the left side and multiply both sides by dt. And so we'll see, we'll get dv over this whole thing, g minus k over mv squared, equals dt, 1 dt. Okay, now to tackle this integral is kind of gross, because what you've got is a squared power in the base, so we're going to have to use some messy algebra to get there. This is where I'm going to say I recommend just reading through the nicely formatted solution on page 42 to 44 of our textbook, because I want to pause and show you an example where we won't lose the thread just because of the algebra of the integral. Okay, we're going to do a different one that will show you just the process of separable equations on its own right. All right, so let's say we have the initial value problem where u prime equals cos of t times u of t with u of 0 equal to 1. Okay, so here we can tell this is separable. I don't have any like added terms on the right. We can see we have a product of a function of t, g of t, and h of u. Even though this is u of t, really, you know, what is u of t? U of t is really u, right? So we are good to go here to separate variables. How do you separate variables? Well, you grab the functions of one variable and bring them to one side, and the functions of the other variable and bring them to the other side, and integrate. Okay, so what we'll see, we'll divide both sides by u, and we'll get u prime over u equals cos of t. So now I've got functions of u on the left, functions of t on the right. That's what we mean by separable. This is what we call separation of variables. And again, this is kind of an ideal way to solve these. As long as you can solve these or set these up in this way, this is great. This is much less complicated than the other stuff we're going to learn this year. All right, so how to solve this? So we want to integrate both sides. You might see, you know, on the left, how do we do this if it's u prime of t and u of t and we don't know what u is? You could go by way of a substitution, or you could recognize, right, u prime is du dt. And so, you know, what you could do is, you know, quote unquote, multiply both sides by dt and be left with du over u equals cos t dt. Okay, and then you can integrate both sides. That's fine, you know, to do that. Or, you know, you can start from here and integrate both sides with respect to t, and you'll end up at the same place. Okay, but at any rate, integrating the left-hand side, we'll see that this is a natural log. And on the right-hand side, this is sine t plus c2. Again, we'll collapse those constants of integration. Just be sine t plus c. We'll know that c is c2 minus c1. And to solve for u here, we will raise both sides as powers of e. So then the left-hand side will cancel out. We'll be left with absolute value of u equals e to the sine t times e to the c. And the idea here is you do have to treat this absolute value. Since this is always positive here, this e to the c, then I can drop this absolute value by just making this itself a constant. All right, calling this c, which can now be positive or negative, that now equals u equals c to the c times e to the sine t. Wow, speaking's hard. Okay, so we had a initial condition here because this was an initial value problem. U of 0 equals 1, I believe. So this tells us that, you know, u p of 0 equals 1, which is c e to the sine of 0. So this is all telling us that c equals 1. So then u p of t must just simply be e to the sine t. Okay, so now here You might notice that this is a linear equation, so you could use the method of integrating factors if you got it into the right form, and you should end up at the same place, okay? And you're invited to do that to just kind of verify and make sure you're not going crazy. There's multiple ways to get there sometimes, and that both methods should work out. But in general, the difficulty with these problems is not getting started. It's when you get to this point, knowing how to integrate. So you're going to need to review integration rules. Each problem will be different, and you're welcome to use tables and things like that to help you get through it. So I want to do one more example of a cool application that we'll see again and again, and then we'll call it for today. Okay, so here we're going to look at Newton's law of cooling, which again is easily described with differential equations, and then we can solve it however we get lucky enough to solve it. So let's start with kind of how we might think through modeling this with an ODE. So the idea is that the temperature change is proportional to the difference in an object's temperature and the ambient temperature around it. So we have to assume, maybe something's got a single temperature throughout. We know your fingertips are probably not the same temperature as the core of your body, but to simplify the problem, we need to kind of unify that. So for a given object, how it's going to cool based on the environment, the surrounding temperature, we have to assume that it's going to be proportional to the difference between its own temperature and the ambient temperature. Okay, so we can start giving some things some names. Usually, what we're after something that would tell us the object's temperature at time t. Temp of object at time t. And the temperature change, right, is the rate of change of the temperature. How it's changing, again, this is the easy thing to describe. How it's changing is proportional to the difference in the object and the ambient temperature. Well, we'll need to say that the ambient temperature, we can call it a function of time if we want. This is the surroundings. This could be a function of time, or we can assume it's constant based on what we want to do. And so we have and we're going to need a proportion, a constant, proportionality constant is how we say that, and so we'll call that K. And so we have all the names of things. Now to build this, all right, the change is proportional to, so the way I'm reading this is the change, the rate of change u prime of t is proportional to the difference between the object and ambient temperature. So proportional to meaning scale this quantity. What is that quantity? The difference in the object, which is u, and the ambient temperature, which is a. So u minus a. Okay? So this is writing this sentence in the language of differential equations. Rate of change is proportional to the difference between the temperature and the ambient temperature. So a couple of things. Here we're going to treat a like it's constant. Maybe it's not changing enough that we care to make it a function of time. Just know that it can be. Since this is cooling, a couple things are of note. If this is cooling, we have to assume that the object's temperature is warmer than the outside, right? It's not adjusting to, it's not warming up because it's warmer outside. The object itself is warmer than the ambient temperature. And then if we know that this is cooling, that means that u prime must be negative, so that means that we should throw a negative sign out in front of this k, because again, we normally take k to be positive just for good notation. And so this here is our law of cooling, our ODE that models cooling. Okay, minus k times u minus a. And at this point, you're like, Mally, this is tremendous. This is very, very cool. What does this have to do with separable equations? Well, we can solve this with separable equations. We can say we can find a general solution. using separable equations. So if this is u prime equals negative k times u minus a, if a is held constant, sometimes my k's look a little weird. If this a is held constant, then I can treat this as a function of time, my g of t, and this here can be my h of u. Right, u minus a is a function of a. So then I'll have u prime over u minus a equals negative k on this side. And now I can go through and do the thing. And so we do it. Integrate both sides with respect to t. We'll get the left-hand side is natural log of u minus a equals minus kt plus a constant of integration. All right. From here, similar to before, raise both sides as powers of e. We'll get u minus a equals e to the minus kt times e to the c. Let me go to the next page here. All right, similar logic before. We can drop the absolute value and just call this a constant that can now be positive or negative. And then we can add a to both sides. So u of t is really a plus c e to the minus kt. So this is the general solution, and we'll unpack this in a moment. Let's say if we had the initial conditions that, u of 0 was some u naught, okay, whatever the initial temperature was, let's leave it general. Then what this would tell us is that up of 0 is u naught, and this is equal to a plus c e to the minus 0, right? So this tells us that really c is what? U naught minus a. Therefore, our particular solution, given an initial temperature of the object, would be a plus u naught minus a e to the minus kt. All right. So here's our particular solution. Now, why does this make sense? I want you to hit pause and take a look at this function for a moment, because again, my goal is for us to be fluent in reading these things. So why does this make sense? And then I'll give you my take. Okay, so hopefully you're playing along. It's going to be better if you can. The temperature of the object is u as a function of time. What do we see? We have a constant a. This is the ambient temperature. And this is, constant here. And then what do we see over here? We have this decaying term. Why is it decaying? K is always positive. It's negative up in the exponent. So this thing in the long run is going to 0, right, as time continues, which means the difference between the two is being shrunk down to nothing. And where it starts at t equals 0 is at u naught, right? So we have the ambient temperature outside, we have the starting difference between the two, and this is scaling it down to nothing over the long run. We also call this whole thing the transient term. Transient meaning it's leaving. Okay, it's going away, and we'll eventually be, in the long run, left with just the ambient temperature. Okay, which makes sense. All things will kind of tend toward the temperature that it is outside. That beer is getting warm, that coffee is getting cold, whatever it is. Okay, so just to recap, kind of the point of this was to show you, again, it's easy to describe things in terms of differential equations, to describe a problem. It's hard to solve to find what that is, but here we're able to use separation of variables, that technique, to do so. So that's it for this relatively easy section. And make sure you reach out with any questions that you have. Enjoy.